Hi everyone, my name is Yuanqing. I'm from University of Wisconsin-La Crosse. I'm a graduate student major in software engineering. Dr. Chen and Dr. Zheng are my advisors. Our project is developing an autonomous driving model based on Raspberry Pi. This presentation is organized by these 5 parts: objectives, background, data collection, training, and results. Now, let's start with the objectives of our project. In this project, we train a convolutional neural network based on the VGG16 using the lens image frames which are obtained from a front-facing camera mounted on a robotic car. We then use our trained model to drive the car in a predefined environment. The model will give the steering commands, such as forward, left, and right, to make the car drive in the lane. The path to self-driving vehicles has been a long and winding one. There are some milestones in the development of self-driving car. In 1925, the inventor Francisco Holtner demonstrates a radio-controlled car, which he drives through the streets of Manhattan without anyone at the steering wheel. In 1969, John McCarthy, one of the founding fathers of artificial intelligence, described something similar to the modern autonomous vehicle in an essay titled Computer-Controlled Cars. In the early 1990s, Carnegie Mellon researcher Dean Pomerleau writes a PhD thesis describing how neural networks could allow a self-driving vehicle to take in raw images from the road and output steering controls in real time. In the decade of the 2000s, self-parking systems began to emerge, demonstrating that sensors and autonomous road technology In the decade of the 2000s, self-parking systems began to merge, demonstrating that sensors and autonomous road technologies are getting close to ready for real-world scenarios. Starting in 2009, Google begins developing its self-driving car project, which now called Waymo. By 2013, major automotive companies, including General Motors, Ford, and others, are all working on their own self-driving car technologies. An example of self-driving model is built by Intel Intelligent Systems Lab. They operate on a semantic map rather than raw sensor images to output waypoints. After that, they use the output to actuate the vehicle by a controller. They also verify the driving policy can be transferred from simulation to reality. NVIDIA company also published their work on training an end-to-end self-driving model based on the raw road frames. They trained their CNN model by using the raw picture of road pictures as input to predict the steering wheel angle of the car. Their contribution on the self-driving car provides us the basic idea for training our model. Here is a picture of the robotic car we used in our project. This robotic car is a product of some founder company. It's based on Raspberry Pi 3 Model B. The Raspberry Pi is the core controller of the robotic car. It connects with a motor driver and a servo controller to send the speed and direction commands of the robotic car. It's also responsible for the Wi-Fi as well as the camera connection. In this project, we tried 2 different types of cameras, a USB camera and a Pi camera. Comparing the captured images, we eventually decided to use the Pi camera. The main reason we choose the training datasets collected by Pi camera is that the Pi camera provides the lens frames with a wide field of view, while the web camera's front end blind spots almost the two lengths of the robotic car. We kept the camera position and angle unchanged in doing our project. Although there were many large-scale open datasets for self-driving, such as Waymo Open Dataset and Berkeley Deep Drive Dataset, these datasets are used for a real car to do the object detection and tracking. They are usually used to output the steering angle for the car. However, the robotic car we used can only remotely operate it by receiving forward, backward, left, or right commands from a client, which is different from a real car. So we need to collect the dataset by ourselves. The SoundFounder company provides Python programs to control the robotic car remotely. Like in the client, when the user presses key on the keyboard or clicks the control button on the user interface, the server end of the car will receive the steer commands and send these commands to the server controller to control the motor of the car. To collect our dataset, we modified the client a little bit. We kept the steering button in the interface and added a new button, Begin Self-Control, for the self-driving mode. When we collect the datasets, we use forward, left, and right buttons to save the steering commands and the associated image pictures. We didn't use the home button and backward in the data collection process. The home button controls the direction of the tire. After the robotic car turns left or right, pressing the home button will straighten the tire direction. Due to the fact that we only mounted one front-faced camera in the robotic car, we didn't change the model to do backward prediction. This is our modified user interface. We manually operate the robotic car drive in a place where we draw the line on the ground over 2 hours to collect the dataset. We collected a bunch of line frames and the corresponding commands as their labels. We split the labeled line frames into training, validation, and testing sets. In order to have a clear baseline of the testing accuracy, we keep each set contains the same number of images in each action class. Here is the dataset distribution. When we use these line frames to train our self-driving model, we found some shortcomings. The background, like sofa and chairs, they may cause noise. Besides, we only need the self-driving model to learn the lane feature in the image, which means only the bottom half of the image is useful. Therefore, we consider doing data pre-processing in the project. In order to focus on the region of interest, which is the lane in each frame, we cropped out the top half of the frames to remove the chair or sofa from the image. In the process of training the self-driving model, we found the model will affect by the light situation. To solve this problem, we tried to revise the color of each channel in the image. The reason we didn't grayscale the image is that grayscaling will convert red, blue, green 3 channels into one. Like using OpenCV API, the image will convert RGB 3 channels into one by using the color BGR to gray function. In our project, we still want to keep the 3 channels information. So we tried to generate the revised pixel value of 3 channels by this formula. The left are the lens frames captured by the Pi camera. The top right are the images after cropping the top half of the lens. After cropping, we also revised the 3 channels value. In this project, we use the dataset after data processing. Comparing the prediction results with data preprocessing and without preprocessing, we believe it's helpful to do the data process. In order to map the lens frames with the steering commands, we choose the CN architecture because CN is the most popular deep learning architecture inspired by the visual perception mechanism, which is widely used in computer vision and natural language processing. In addition, there are many pre-trained CN models in image classification, like VGG16, ResNet, MobileNet, etc. In this project, we choose Keras to train the model, which is a widely used Python deep learning library to train our model. In addition, we train our model on Google Colab because they provide free TPU resource, which is significantly speed up the training time. In addition, we also use the transfer learning in this project. Generally speaking, transfer learning is the process of using the information learned from one neural network into another neural network. The reason we use transfer learning is that the image set collected by ourselves is relatively small. It's easy to overfit and stock at a low accuracy. So we won't use pre-trained CN model as a feature generator to improve the steering command's prediction accuracy. The objective of this project is to map the lens image with the steering commands from the forward, left, right list. We found this goal can be achieved by using image classification technique. So finally, we choose one of the popular image classification pre-trained model VGG16 and tuning it to achieve our goal. The prediction model is based on VGG16. Basically, it totally has 13 convolutional layers and 5 max polling layers. We added 1 flattened layer, 3 dancing layers, and 2 dropout layers before the output layer. Here is the overview of the architecture. The white layers are the structure of VGG16, and the blue ones are the layers we modified. We use the training set to train our self-driving model and use validation set to evaluate and tuning the weights of each layer. The model will output a vector of 3 steering commands probabilities. The robotic car will eventually choose the steering command with the highest probability. We sieve the model weights and model architecture together into a H5 file. The reason we saved the model in a H5 file is that this format can save data in a hierarchical way. In addition, it's also supported by the most popular open-source machine learning platform TensorFlow and open-source neural network library Keras. Besides, we also saved the class label into a Python Pickle file. Python Pickle module is used for 7 objects by serialization. It could be easy to reload and get the same class sequence which was used in training process. We tested the self-driving model online and in the real world. In order to have an overview of the model performance, we tested the model online using the test set. We feed every learned image into the model and get the predict output. After that, we compared the output with the actual label of the image to get the accuracy of the model. we trained the model by using different amounts of images. We named these datasets as Pi00, Pi01, and Pi02 dataset. We found that the test accuracy was not improved by increasing the number of training images. This is a problem we still need to figure out. We also tested our model in the real world. We deployed the model on the robotic car and drew the line on the ground to test it. We tested the model in two different road conditions, with carpet and with floor tires, as well as different lighting conditions. Unfortunately, only in some cases, the model can successfully drive the car complete the test. Like when we tested the model drive on the carpet ground, we drew a line with a 1.6 meters long and 0.25 meters width. If the straight line followed a right curve. With sufficient lighting situation, the model can drive the car follow the straight line and pass the right curve. When the car approached the end of the lane, the model mispredicts a little bit and drove the car rushed out of the lane. Same road with insufficient lighting situation, the model almost cannot drive the car past the right curve. When we tested the model drive on the floor tire ground, we drew a left curve followed a straight line with 1.97 meters long and 0.25 meters width. With sufficient lighting situation, the model can drive the robotic car finish the test successfully. However, under insufficient lighting situation, the model drove the car overlapped the left lane. More detail can be found in our paper. Finally, I want to say, this project provides me the experience of training a simple autonomous driving model based on machine learning. We also tried different data processing methods. Comparing the online testing accuracy between the model built by ourselves and the transfer model, we found that using transfer learning can help in the model improve the prediction accuracy. Comparing the online testing accuracy between the model built by ourselves and the transfer model, we found that using transfer learning can help the model improve the prediction accuracy in our project. In addition, in the approach of improving our model, I also learned the basic skills to do the error analysis. For future work, we plan to collect more data and train the model to recognize obstacles or crossroads. Continue this project, I would like to explore more machine learning techniques. Thank you for your listening.